Group 16 elements NCRT line to line. We will be discussing the most important lines: oxygen, sulfur, selenium, tellurium, and polonium. These are the elements. These are also called chalcogens. The name is derived from the Greek word for brass and points to the association of sulfur and its congeners with copper. Most copper minerals contain either oxygen or sulfur. Frequently the other members of the group, that is not important. So two lines, chalcogens and the names of the elements, that's all. Oxygen is the most abundant element on the earth, 46.6% by mass. Dry air contains approximately 21% oxygen by volume. The abundance of sulfur in the earth crust is only 0.03 to 0.1, means very, very less. The compounds are gypsum, CaSO4 2H2O, Epsom salt, MgSO4 7H2O, barytes, BaSO4, and galena, PbS, zinc blende, ZnS. You can expect these in matching. Copper pyrites, CuFeS2. Traces of sulfur volcanoes, this is okay. Organic materials like eggs, proteins, garlic, onion, mustard, hair, and wool contain sulfur. So majority things are there. Not so important. Polonium occurs in nature. Polonium occurs in nature as decay product of thorium and uranium salts. Yes. The general electronic configuration is NS2NP4. Ionic radii and atomic radii increases down the group. Oxygen atom is exceptionally small. Ionization enthalpy decreases down the group, expected. Lower ionization enthalpy than those of group 15. We know group 15 is having extra stable half-filled configuration. Compact nature of oxygen atom, the electron gain enthalpy is very, very less. Oxygen is least in this group. Highest is sulfur, last is oxygen. Electronegativity, oxygen has the highest electronegativity after fluorine. Decreases down the group, regular point. See, oxygen, sulfur are non-metals. Selenium and tellurium are metalloids. Polonium is a metal. Polonium is radioactive and short-lived half-life is 13.8 days. All these elements exhibit allotropy. Melting and boiling points increase with increase in atomic number down the group. The large difference between the melting and boiling points of oxygen and sulfur may be explained on the basis of their atomicity. Oxygen is diatomic, whereas sulfur is octatomic. Octa, hexa, diatomic also. Oxidation states, general oxidation state is -2 because of 2 electrons, and -2 oxidation state down the group decreases. Polonium hardly shows, right? Oxygen shows generally -2 oxidation state. Some exceptions are there. That exceptions are OF2, where it is +2, and other elements are going to show +2, +4, +6, but +4 and +6 are more common. The stability of +6 oxidation state decreases down the group, and +4 oxidation state increases. Inert pair effect. In this group also inert pair effect can be noticed. Before going to anomalous behavior, just have a look at here. Oxygen electron gain enthalpy is least than others. Okay, now this will be coming here, least. Remaining all are okay. Okay, now regular trends are there. Regular trends. Electronegativity, regular trend. Nothing special. Nothing special, right? So coming to anomalous behavior of oxygen. The anomalous behavior of oxygen, like other members of people, are small size and high electronegativity is the reason. Water, hydrogen bonding, which is not found in H2S because of small size. The absence of d orbitals in oxygen limits its covalency to 4 and rarely exceeds 2. Coming to reactivity with hydrogen, all the elements of group 16 form H2E type, like H2O, H2S, H2SE, H2TE. Okay, The acidic character increases from H2O to H2T. That can be explained in the decrease of bond enthalpy. Thermal stability of hydrates also decreases from H2O to H2PO. All the hydrates except water possess reducing property. Water is not a reducing agent, and this character increases from H2S to H2T. See the specialty here, it should be melting point should be lowest, but it is highest because of hydrogen bonding. Boiling point highest because of hydrogen bonding. Rest properties are regular, you can check. Water bonding is 104 because of sp3 hybridization. These three are 92, 91, 90 because of pure orbitals. Bond energies and all you can check, nothing special about that one. Dissociation constant, you can see this is very less, so this is not so acidic and this is good acid. Reactivity with oxygen, they form EO2 and EO3 type of oxides, where E is all these elements. Ozone and sulfur dioxide are gases, while selenium dioxide is solid. Interesting. O3 means O2 type. O2 and SO2 are gases, and selenium dioxide is solid. This one is interesting. Reducing property of dioxide decreases from SO2 to TeO2. SO2 is reducing while TeO2 is an oxidizing agent. And along with EO2, they are going to form EO3 type of oxides also. SO3, SeO3, TeO3, both type of oxides are acidic in nature. We'll change the color. Okay, now, yes. Reactivity towards halogens. Elements of group 16 form a large number of halides of the type. These are the types. The stability of the halides decreases in the order of F minus, Cl minus, Br minus and I minus. Hexafluorides are the only stable halides. SF6 is exceptionally stable for steric reasons. They have octahedral structure. SF4 is a gas, SEF4 is a liquid, and TEF4 is a solid. sp3 dehybridization and have trigonal bipyramidal structures in which one of the equatorial positions is occupied by a lone pair of electrons, so it appears to be seesaw geometry. Dihalides of sp3 hybridized. Tetrahedral structure they have. S2F2, S2Cl2, S2Br2, Se2Cl2, Se2Br2, all they have open book structure like hydrogen peroxide. They undergo disproportionation reaction. Very important. So coming to dioxygen, this is not required now. Properties are also not required. Simple oxides, yeah, this is regular point, so you can read this one. A binary compound of oxygen with another element is called oxide. Yes, MgOAl2O3 are simple. Pb3O4, Fe3O4 are mixed. Pb3O4 means it is a combination of PbO and PbO2. Fe3O4 also same, Fe2O3 and FeO combination. Acidic, basic and amphoteric character. An oxide that combines with water to give an acid is known as acidic oxide. SO2, Cl2O7, CO2, N2O5, all this. SO2 combines with water to form H2SO3. SO3 if you are taking H2SO4. Non-metal oxides are generally acidic, but few are having some special characteristics. Metals have high oxidation state, also have acidic character. These are all acidic in nature. Basic oxides examples Na2O, CaO, BaO. CaO combines with water to give calcium hydroxide, a base. In general, metal oxides are basic. Some metal oxides, both acidic and basic oxides, that show dual behavior. They are called amphoteric oxides like Al2O3, ZNO, zinc oxide also you can take. There are some oxides which are neither acidic nor basic. Example CO, NO, N2O. They are known as neutral oxides. Then coming to ozone, this is about ozone. About ozone, 1-2 points are important. Pure ozone is a pale blue gas, dark blue liquid and violet black solid. And ozone, we know the formal charges. This oxygen will be having formal charge of -1. It is +1, this is 0. Okay, formal charges are also very important. Sulfur allotropic forms. This is again there in the syllabus. Yellow rhombic sulfur alpha, monoclinic beta sulfur are the most important one. The transition temperature is 369 Kelvin. Okay, now here that is maintained. Below 369 Kelvin alpha form, above 369 Kelvin beta form. You need to remember this. Rhombic sulfur, nothing special in this, nothing special, nothing special. Insoluble in water but dissolves to some extent in benzene, nothing special. Readily soluble in CS2. No questions can be asked on that. It is soluble in CS2. I am saying no questions, but I am underlining that. Don't worry much. Yes, this is important. Alpha sulfur is stable below 369 Kelvin and transforms into beta stable above this. At 369 Kelvin, both the forms are stable. This temperature is called transition temperature. At 369 Kelvin, both the forms are stable. This temperature is called transition temperature. Nothing special. S8 rings, crown shape, and S6 you can see here. This is, I think you remember, cyclohexane. Similar to cyclohexane. This is chair form, and we have S2. S2 species is paramagnetic like O2, which is available around 1000 kelvins. Yes, these are known to you. Sulfur dioxide not required. Oxo acids of sulfur not required. Sulfuric acid not required. At present, they are all out of syllabus. Only general properties we need. That's it. Thank you. This is Lucky Sir.